Well, it's time. Welcome back, folks. So for today's class, to close out week 11, we're going to be working through section 7.2, the more about modular arithmetic section in number theory, and then extending the work that we're going to look into, the Euclidean algorithm on coming up with the greatest common divisor, into primality, relative primality. Also, the bigger announcement is probably that we have exam 3 coming up. It's going to be on Tuesday, April 14th. And so getting into the same routine that we did for exams 1 and 2, on Friday, I'll be writing out the formula that's going to be attached to the real exam 3. The exact sections will be on the exam, as well as the sample exercises, just like we did before. But any questions or comments at all, folks, before we get started today? Okay, well, let's jump in. In this section, 7.2, we're going to be looking into two interesting algorithms, the mod and div algorithm and the Euclidean algorithm. Our author has the pseudocode written out for both of those two particular algorithms, but the code right here you can think of as just being expanded pseudocode, and it's pseudocode that just happens to also run in R using RStudio. So if you like, you can use that or whichever similar program that you would like to use, say Python or C++ and so on, to demonstrate how this code works. So first, we're going to take a look into the mod and div algorithm that's displayed here. This is our author's really short pseudocode for how this runs. But before we jump into that, it's good to kind of take a step back and see what it's all about. All we're really doing is implementing an algorithm for coming up with the modulus of a set of numbers. And there's a div part that's kind of confusing about this algorithm. It returns two values. So another thought of what this algorithm is all about is working with the so-called division theorem that we did last class, looking into two examples. So as far as the division theorem goes, best way to think about it is just put down our by hand formula for modulus. If we were doing by hand n mod k, and say maybe it's a large value n, or maybe n is negative, but we want to be extra sure that we have the right value, the formula would go n minus k times the floor of n divided by k. So that's our handy go-to formula whenever we're wanting to be extra sure what the value should be for n mod k. As always, it's just the remainder after division by k. But now that we have that, what n mod k represents in the division theorem above is this r value right here. The floor n divided k portion represents the value d in this theorem as well. And the key idea about this division theorem is these integers will always exist, no matter what n happens to be and what k happens to be in this equation down below. And even more importantly, these values are for the modulus, d for the floor, or the number of times that k will go into n, is also unique at the same time. So we look into lots of ways to think about modulus. Any questions at the moment, just with the refresher on the division theorem and the formula to the right? Okay, well, the next idea with this algorithm here is now we wonder if we had a really large value here and we just wanted to automate this whole process, what would this look like if we tried to implement this? And that's what this pseudocode is all about. We're going to actually use this code, call this function when we're looking into the Euclidean algorithm. We'll extend the Euclidean algorithm even further when we are looking into relative primality. And so this is the start of a long set of basically a house of cards. This is the very bottom row. So the idea is we're going to input integers n and k, playing the same exact role as in the division theorem or in this equation down below for n mod k. The output will be n mod k itself. So we're going to return a value r, as well as the floor. So we call it mod and div possibly motivated by the division algorithm. So it returns both the modulus and the floor for two outputs. And here's what it would look like if you're trying to implement either the division theorem or just n mod k itself. We initialize r to be n, this part where k is dividing into n. We set d 0, and then we just construct a really interesting while loop. While r is larger than k or equal to it, we redefine r. R is defined to be r minus k, and we increment d by 1. Then, as soon as r violates this inequality here, we exit the OR loop, and we just return whatever r happened to be after doing possibly multiple subtractions, and whatever d comes out as after starting at 0, and it increments by 1 every time we loop through the while loop. So somehow, some way, this algorithm here is just the same as doing Edmond K. This is just the machine way of doing it. What we'll do to really understand exactly how this is going, justify what's happening in the while loop, is we'll trace it out for a particular example. So that's what example 5 is all about. And then part B is just referring back to the division theorem, telling us what the values R and D are giving us once we run this. I did make a revision on the notes. I practiced this on, I think this was Tuesday morning, and I felt like we're looping through while too many times. I think it came out as 8 times looping through. That got pretty tedious. So I changed the number here just to keep it a little bit more reasonable for doing this in class, more similar to what you'll do in the homework as well. Well, any questions, folks, before we trace this algorithm? Okay, well, we've done this kind of stuff before. It's not too different from, say, when we first wrote pseudocode for a summation notation and then traced that. What we'll start with is the execution of mod and div for the particular values n and k. So first, n mod k. Let me write it this way: mod and div for 39 and 8. It's not a bad idea to put just a quick note that when we put in these arguments to the function that we're calling, n is 39 and 8 is k, to help us trace through the algorithm that we see here. So once we run this, we're going to just trace through the very short code we have here. And the very first step we take a look into is we define our n and d values. We're defining what this is going to start out as and what this is going to start out as, and they're going to work up to its ultimate computation. So initialize by saying r is defined to be n, which is 39. At the same time, d is defined to be 0. So we're done with that step, and then we're on our next level, tracing the code. We're 25% done in a certain sense. On line 2, we hit the while loop. So let's write this as our second step. Check the condition, the logical condition, to see if we even enter into this while loop whatsoever, is see what happens with r. R is currently set to a 39, and when we check 39 against the k value 8, this is greater than or equal to k, which is 8. So this tells us we do in fact execute the while loop. So I'll write here as a quick note: while loop executed. And then once it executes, we are going to do this operation here. So we're going to change the value of r, change the value d, then we'll loop back to the while loop, check the logical condition, and see if we leave or if we have to loop again. So let's update these values. Since the while loop is executed, we have that r is now defined to be, let me fix that notation there. If you use ordinary equality, I wouldn't be super picky about that, but this defined to be equal symbol is pretty nice to have, because mathematically, this is just our strange statement to write. If this was an ordinary equality, you're saying just k is 0. But we mean something different. We're just saying we're redefining the r value to be now r minus k. R still set to be 39. K will be 8 for the entire process. So now r is set to be 31. then still at this level here, we redefine D. D is defined to be itself increment 1, and that's always going to go the same exact way. It's initialized at 0, so this is just going to be 0 plus 1, for a value of 1 altogether. And, well, once we're done with that, we ran through the while loop, but since it's a loop, we check this condition once again to see if we truly exit it. But any questions so far, folks, getting to this stage of the trace? Okay, again, sort of like what we were doing when we were proving, say, our recursively defined pseudocode actually works as intended when we were using strong induction. This time we're just doing an honest trace, no proof technique whatsoever, just following this as literally as possible as it's written down. So with our values incremented and redefined in this way, we go back to line 2 and make another logical check. So I'll call this step 3, where we're back at line 2. We see what the value of R is. R is equal to, it's updated to 31, which is still greater than or equal to the K value, which is set to 8. Since this condition passes one more time, and it'll pass a couple more times, we can say the while loop is executed, which means we run this once again, and then it starts to become pretty methodical along the lines. That's, again, one of the reasons I dropped this value a little bit lower, so it didn't feel like we were doing this all day. So let's run through this. R is now defined to be R minus K. And if you skipped that part right there and just went to, say, 31 minus 8, that would have been just fine. And let me fix my notation once more. Defined to be has a little equal sign there. R is defined to be R minus K, but we're using the updated R value at 31 minus 8. So now we're at a value 23 altogether, still greater than or equal to, or hang on, I'm jumping the gun on that, to the while condition. We're just incrementing this, decreasing this to 23. So that part right there, increment the D value. D is defined to be equal to, once again, D plus 1. So now this time it's a 1 plus 1 for a value of 2. So we use the prior value of D that's stored, which was 1. But again, all that's going to happen with this D value is it's just growing step by step. Then we keep on going until we exit that condition there. So here's our next line. R is now set to 23, which is, forgot equality there, greater than or equal to K, which is equal to 8. So this will end at some point, right? This cannot go forever. There's no way that this is an infinite loop. So the while loop is executed. And we know exactly what it does. R is going to decrease by the K value. R is now equal to be, or defined to be equal to R minus K, which means this time it's 23 minus 8 for a 15. D, if you just say it's strictly equal to 3 because we know how it goes, that's just fine. So let's maybe do this one more time. It's defined to be D plus 1, which is going to be 2 plus 1 for a value of 3. And then, oh, that comma came along for the ride. Let me fix that. Then we check the while condition again. We're getting there. So on step 5, R is now 15. But 15 is still greater than or equal to the K value, which is 8. So the while loop is executed again. But let's take a step back on what we're really doing here. When we're thinking about this N and K value, we're really just doing a modulus operation. And we know that 8 is going to go into 39. Well, that should be 4 times, right? 8 times 4 is 32. There should be a remainder of 4. But if you say divide it into it took away one value, subtract 8 from here, we're thinking of it, say, dividing into it once, even though that's not perfect logic there. If you subtract 8 again, we're thinking of it having divided in twice. Subtract 8 3 times, and we're thinking of it, that k value of dividing in 3 times, and do it one more time, and it would have divided in 4 times altogether. So that's what this value is providing. It's just doing it in a really step-by-step methodical way. So when the while loop is executed again, we're back here. R is defined to be equal to. We can say R minus K, or just jump the gun to that. R is 15 minus K, that's going to take us to 7. D, we can say D plus 1, but we know we're just adding 1. So if you did this on paper and just said 4, again, that's completely fine as well. Let me make that look more obviously like a comma. Then finally, once we're at this stage, we have done the incrementing in the while loop. We go back here to check this condition. On step 6, we have R equals 7, but this time that's strictly less than K, which is 8, and so we're bypassing the while loop. So pass the while loop, or let's say skip the while loop, however you'd like to express this. Skip the while loop. That logical condition, R greater than or equal to K, fails, comes out as false. That means we don't do any incrementing whatsoever here, and we're just going to return the values. So that takes us to step 7, return. Whatever R landed on, it was 7. So we're going to return R7. And we'll also return D is 4 from that prior step. So we've done more than just the modulus. We also exhibited what the floor is of 39 divided by 8. That floor has to come out as 4. And if we divide 39 by 8, this is also saying the remainder is 7 altogether. So again, this is yet another look of what modulus could be implemented as, how to compute with it. But the major purpose of doing all this is to think about how the division theorem works and to give a really fast algorithm for producing those two key values in the division theorem. But for the moment, the problem is all about the trace. Any questions at all, folks, tracing that syntax? Okay, lots to write down, even though while loop only executed 4 times, it feels like it's a little bit tedious after a minute, but we'll get some good practice with these kinds of things. So next, we're going back to the division theorem, or the division algorithm, if you prefer to call it that way. It says verify that KD plus R equals N as required by the division theorem. And that's what the division theorem tells us. There will exist a particular value D, that's the floor or the number of times that K went into N, and it will also produce the remainder R. Let's also get the original values. N is 39, K is 8. So not much to do in this last step. It's just reminding us about the division theorem here. We can say KD plus R equals N means place in the value for D, the value for the modulus, which we're just calling R. We'll have 8 times 4 plus the remainder 7 must be exactly equal to N, which is 39. But that looks about right. That's 32 plus 7, giving us a 39 altogether. Well, we did it, folks. That's our third look into using the division theorem, and yet another look at how to think about and work with modulus. Any questions or comments at all getting through this one? Okay, well, here's once again the overall pseudocode that the author provided. for this entire process. One thing I felt was pretty interesting about this pseudocode is he specifies n has to be non-negative right here. N is greater than or equal to 0, which seems kind of counter to what we did in chapter 2. We made a big deal in chapter 2 that n can in fact be negative. Our formulas that we gave for modulus in that chapter handles a negative value, and we did lots of those computations. We did one on these notes, in fact. So I felt like it was a good idea to just extend this pseudocode. If you go back here, this pseudocode for mod and div also handles the case when n comes out as negative. So here's what it looks like imported into RStudio. The if part right here is just this original pseudocode. It gives the while case, does the subtraction, does the increment by 1. It'll return the same values. I put C here to say combine R and D for the overall return as a vector. But if R is negative, we know that we can compute the modulus still. And this is the adjustment. You go from minus K to plus K. And instead of incrementing by 1, you decrement by 1. And it handles modulus just fine with that small adjustment right there. And so if you wanted to play around with this, here's what it would look like in this problem. N is 39 and K is 8. Go mod and div 39, 8. And it gives us the 7 and the 4 that we're expecting. If we want to test it on negative values, we have something ready to go up here. We did negative 42 mod 17, and we found a R value and a D value again. So go mod and div, negative 42, 17. And that's the 9 and negative 3 that we're expecting. It's pretty basic code, so you have to know what the outputs mean, that the first output is the modulus, the next output is the floor. But with that information there, this can be kind of a handy tool to use to check your work. Say as a homework question, if you're doing a trace and the numbers are maybe a little bit larger, you can just check it really fast using this. But you can also just use any good coding program will just give you pre-implemented a modulus function and a floor function. This one's just special because it's built from our author pseudocode. Well, the next things we're going to look into is just more topics on number theory relating modulus specifically. We're going to look into congruence. This will be helpful for us when we look into a new algebraic structure in 7.4. And we'll also look into more properties of modular arithmetic. So this loops back to a comment made from a student way back in our section 5.2 during ordinary induction. We did an induction problem where we were looking into divisibility by 6. I think the homework question was divisibility by 5. And what great question was, could we redo this whole proof by just focusing on modulus itself without saying there exists a K such that the way we wrote out our divisibility property. This is giving us the tools in the language, the congruence here definition, some extra tools down here to make that proof happen. So if you're curious on how that goes, let me know and I'm happy to write it up as just a second take on that section 5.2 induction proof. So here's our brand new definition. Modulus has surprising amounts of algebraic structure. We'll see even more in section 7.3 and quite a lot in 7.4. And here's the next thing we're going to look into. Congruence modulo k, or just congruence mod k altogether. We take any two integers a and b, we'll say that they're congruent mod k by writing out this statement. The type of equality altogether, we put down triple bars to say, not your ordinary equality. This is something that we're going to look into even more closely in chapter 8 with relations equivalence classes. This is an equality as far as congruence goes. So we have to indicate the k value as well. We'll say A is congruent mod k if A mod k equals B mod k. So if they have the same remainder after division by k. So really, it's just a quick definition. We'll work more and more with it in the next sections on number theory. But first, we'll just practice a little bit more with this before looking at the other properties. Any questions at the moment, folks, with defining congruence? Okay, again, chapter 7.2 is kind of strange because it has a lot of kind of unconnected for the moment topics. So we're going to work with congruence a little bit here on this one example, and then this will be a topic that we come back to when we're further on in chapter 7. So for the moment, we're just checking the definition. It says determine if the congruences are true or false. First one is congruence mod 5. So we want to know if 73 is congruent mod 5 to 3. If these are considered a type of equality under the mod 5 operation. But really all we have to do is say, take 73 mod 5. Mod 5 is kind of nice because when we divide by 5, if it goes in evenly, the number has to end in either a 0 or a 5. So it would go into 70 evenly. 73 will have a remainder 3. That means automatically 73 mod 5 is just a 3. That's the left-hand side. That's the A mod K part on this equation. The right-hand side, the B mod K, would take the 3 you see there, do mod 5. 5 does not go into 3, so it has an automatic remainder of 3. And we've just showed the equality. 73 mod 5 is 3, and so is 3 mod 5. If we have equality right here, we just conclude 73 equivalent to 3 mod 5 is true. So we have our first true congruence. Any questions at all, folks, with that fast definition check? Okay, this is the second revision on the notes, this red number here. When I practiced these problems on Tuesday morning, I noticed they were all true, and that's kind of dissatisfying in a certain sense. It's funner if one's false, so we know what made it false in the very first place. So that's the modification there. So trying this all out again, to check this congruence, we'll take 100 mod 12. And there's no harm whatsoever if you're using the ordinary equation. N mod k is n minus the floor of n divided by k. We've used that equation quite a lot in these notes as well. Or you can get just about any calculator. You can get Desmos, it'll do the modulus operator. This one will do it with a predefined function. Let's use our function here that we've already defined. So if you decide to take a shortcut in the homework, that's completely fine. So let's take mod and div 112. It gives us two pieces of the output, but we just want the modulus, the very first output. So I'll index into the output by putting a bracket 1 to say, I just want the first part. The first part is just the modulus, and it says 100 mod 12 is 4. So the remainder after dividing 100 by 12 is 4 itself. Then we go to the right-hand side, take 14 mod 12. 12 goes into 14 once with a remainder of 2. But now these values are unequal. So in other words, we have inequality right here. So this tells us 100 equivalent to 12. Excuse me, let me say that better. 100 equivalent to 4 mod 12 is the better way to say that, is false. And with so many things mathematically, if you didn't say is false right here, if you just went big angry slash through the triple barred equality there, that'd be a fine way to convey the same information. If you did both, no harm done either. Well, you know, if you did both, that's a double negative. That would be saying it's true. So let's do one or the other to not accidentally convey a double negative. Well, any questions at all, folks, on that second definition check? Oh, thanks for that. Yeah, that was a miscopy there. Good eye. 100 equivalent to 14, not 4. Mod 12 is false. Thanks for spotting that. Other questions or comments so far? Okay, and just for the sake of practice, let's do it one more time. We're checking if -5 is equivalent to 3 mod 8. So first operation is to take -5 mod 3. And we can use the calculators before, but let's suppose we're doing this as an actual literal exam question. Let's do it that way just for the sake of practice. If this was an exam question, we might probably treat this one by going, this is -5 minus 3 times the floor of -5/3. Using that ordinary equation for modulus that we do whenever we're a little bit wanting to be a little bit extra sure about the computation, or if there's something a little bit more confusing, like the negative there. So putting this all together, this would become -5 minus 3 times. Then I probably would grab a calculator at this point. We know it's not anything special, but it's nice to have the exact decimal value there. If we round this to say -1.7, there's no approximation here. We still get the exact value through the floor function. -1.7. So the floor of this one is going to be a -2 altogether. So this will be a -5 minus 3 times -2. So that's going to be -5 plus 6 for a value of 1 altogether. I feel like I messed something up though. There's definitely a mistake on this. Anyone spot the mistake with this one? The calculation's okay, but I made one critical error when I did the whole operation. Probably running this one through this one too fast. Let's go to the top on the definition. This is definitely one mistake you wouldn't want to make for sure. It says two integers, a and b. My a is -5, my b is +3. So there's the a and b. Are congruent mod k if a mod k equals b mod k, but the k value, the thing we're actually taking the modulus of, is 8. So when I said -5 mod 3, that's a pretty weird and silly error. So make sure if you're doing this as an exam question, which was the thought on this one, you don't make that mistake. So let's fix this here. That's got to be -5 mod 8 altogether, which means we're taking -5 minus 8 times the floor of -5/8. It's kind of always unfortunate when a mistake causes this many corrections. That's quite a lot altogether. Looks like we're going to get essentially the same value here, but let's recompute it. We're taking -5/8, which is a different value, -0.625. I'll just round this to a -0.6. So that'll come out as a -1. So this is 5 minus 8 times a -1, which is now -5 plus 8, coming out as a revised value 3 altogether. Again, watch out for that kind of mistake there. The modulus we're actually taking is mod 8, if we say congruent mod 8. Well, any questions at all, folks, with that mistake and correction? Okay, now we look into the right-hand side. This one's pretty fast. This is asking us to calculate 3 mod 8 once again, but 3 mod 8 is nothing special. The remainder here is exactly 3. But now we had 3 and 3 matching up, just like in the very first problem. So we can say altogether, this means you could rewrite this and say it's true, or just say briefly, this means the congruence is true. Or if you just put down true, I'd be okay with that, especially if this was an exam, that'd probably be good time saving. Well, that's congruent mod k. Again, this is going to be an operation that we come back to. For the moment, our author is just introducing this as a concept to round up a lot of different concepts in 7.2. Next thing we're going to look into is other properties of modular arithmetic, and then get into the greatest common divisor. Any last questions or thoughts, folks, with congruence? Okay, well, let's take a look into the next concept. in modular arithmetic are these pretty awesome properties. Theorem 7.4 gives us some really great tools for computing modulus by hand. Also, these properties can be used in a lot of other kind of surprising ways. When it comes down to certain extra topics like cryptography, modular arithmetic does get involved, and sometimes you have to use the modular function with extremely large integers. This is a way to kind of break things down and make the implementation of the modulus function much more efficient than what we have here, and it can help out with operations even with the predefined modulus function in any coding system. So these are 4 great properties for modular arithmetic. First property we've taken advantage of already before. For any integer k, k mod k is just 0 outright. But then we can add things mod k, multiply things mod k, exponentiate things mod k, and simplify them in these particular kinds of ways. One thing that's missing here is the operation of division mod k. And there's a particular reason why that's missing. Turns out that one is a little bit extra tricky. We need to think about greater common divisor, which seems kind of strange. We need to think about primality, relative prime. And so it's going to take a lot of work, so the entirety of section 7.3, to come up with the division property. But here's 4 fast properties right away. This could be a potential exam 3 question. If we're doing these kind of problems for an exam setting, be sure, for the sake of getting full credit on these, the point of the problem is to really use the properties to demonstrate understanding of them. So show steps using the properties to demonstrate that understanding. So let's give these a try. And they're pretty interesting in the sense that you could just put that into a calculator, get the output out. But the idea is we're trying to show exactly how these properties go. So the first one, 50 plus 98 mod 9, we could break that down in a nice kind of way. Addition mod k, you don't have to necessarily go with order of operations whatsoever. You can do the modulus of the first input, the modulus of the second input, in this kind of way here, then add that result, and take mod k on the final result. So that's our first big algebraic property with modular arithmetic. Applying it down here, it would look like this. This becomes 50 mod 9 plus 98 mod 9 mod 9. Then the modular arithmetic is pretty fast here. 9 times 5 is 45. So 9 would go into 50 with remainder 5. That means that mod is just 5 itself. Likewise, pretty fast on this one. 9 times 10 is 90. So that means 9 goes into 98 with remainder 8, 9 times. So if the remainder is 8, we just get 5 plus 8 mod 9. And that's a massive simplification of the problem so far. I'm going to say show all steps using the above properties. If you skip from here down to here, I'll assume that you just did the modular part in your head, and that would be a fine amount of work to show. So all we're really doing now is just 13 mod 8. Excuse me, 13 mod 9 altogether. The remainder is 4 after division, and our work is done. So if we have a bunch of summands, if this is many different terms, maybe summation notations being used, same property would apply. Well, any questions, folks, with that property there? Addition mod k.
Sorry, my microphone's a bit slow. Um, what is the likelihood we should memorize these? Or is it just
That's a
good in
great
general to
question.
memorize them?
I would say for as far as these properties here, if they come up in an exam setting, say exam 3, I think that's probably going to be something I'm going to put on the formula sheet. So it's going to be more about knowing exactly how to use the properties, not necessarily memorizing a bunch of stuff completely for the purpose of the exam. Does that make sense with that question there?
Yeah, thanks.
Yeah, absolutely. And yeah, as far as the upcoming exam 3 goes, I'll be posting the notes including that are going to be included on the last page of the exam 3, probably one of the very first things that I do on Friday after getting caught up on all the grading. So that should be probably posted probably around noon, I'd say. Well, next property we're going to take a look into is multiplication mod K. And again, this is starting to fill out a lot of awesome and interesting tools with the modulus function. And so, like we mentioned before, some of the proofs that we've done in the past in both chapters 3 and chapter 5 on chapter 4 on induction could be redone using these properties. I said that weird. Chapters 4 and 5 rather, forgot my chapter numbers. So as far as multiplication goes, mod K, you could do the multiplication right here, 15 by 23, and then do mod 7. But you can also take the modulus of each factor independently. There could be multiple factors as long as it's a finite number of them. Do the mod of every factor, take the modulus of the result after you multiply them, and then your work is done. So again, these go pretty fast. The first step, just to show exactly how the property loops in, this can be rewritten as 15 mod 7, multiplying 23 mod 7. Take that whole result and just mod 7. And that's the short answer to this. In fact, that's pretty fast altogether. If you did multiply this together, and I was doing this by hand, it would take me longer to complete the result. But here, this is just about done. 2 by 7 is 14, so this would have a remainder 1 if we divide 15 by 7. So this part's just a 1. Likewise, 3 times 7 is a 21, so 23 mod 7, we have a remainder 2 after division by 7. So all this is now is just 2 mod 7, but 2 mod 7 is exactly 2, and our work is done. So this is a way to kind of just divide and conquer, whether it's multiple terms, multiple factors, take the modulus of each term or each factor, then do their arithmetic operation in the middle, and your work is done. Just don't forget the final modulus part. Any questions with that second one there? Okay, so when we look at this whole list of properties, property 1, really it's just a given. It's the fact that an integer will go into itself evenly, guaranteed with a remainder 0. So we know that to be true. It's just stated there to formalize the property. And property number 4, it's just a consequence of property number 3. If you take B to be A again, this would be the property that A squared mod K is A mod K times A mod K, but that would just be A mod K to power 2. And this extends to multiple factors. So property 4 is just a direct consequence of the multiplicative property here. So the major properties are really property 2 and property 3. And this is just multiplication in a new notation, exponential form. So likewise, if we're doing 10 power 3 mod 6, this is the same as 10 mod 6 times 10 mod 6 times 10 mod 6, but any reasonable person would want to just write 10 mod 6 to power 3. It's quite a bit more brief. Then mod 6, the result. But then we're just about done. 10 mod 6 is 4 altogether. So this becomes 4 to power 3. Mod 6. 4 to power 3 is 64. And that's even better in a certain sense, right? 10 times 6 is 60. So division 6 into 64 will go in 10 times with the remainder 4. That remainder is a resulting modulus. And so then again, right at that step, our work is done. Well, again, that's a short tour of properties altogether. There's one major property missing. What if you want to take, say, a inverse mod K? So that's the big one that we need extra tools in the next section on primality, relative primality, which is going to require a first discussion of greatest common divisors before we can get to this idea here. So the next section, 7.4, is working to that extra property of modular arithmetic. But we've got a good set already so far. Any questions at all, folks, with those? Again, another set of pretty fast computations. Okay, well, what this all finally takes us into is the Euclidean algorithm. And again, think about what we're going to do next. The Euclidean algorithm, discussion on primes, discussion on relative primality, is all to get number 5 on this list. How do you deal with division, or A inverse mod K? So to get there, we're revisiting some other old tools from arithmetic from back in the day. Greatest common divisor. Here's the definition, just for the sake of putting down something firm and concrete on paper for review rather. When we say the greatest common divisor, we'll have two positive integers in the discussion, an n and an m. We'll call the greatest common divisor that, in this notation, GCD, of n and m. And it's just the largest integer which will divide both of them. So it's the largest integer that divides both n, that's our division notation at the top of the notes, and it must divide m at the same exact time. And
So it's
so,
also known as the greatest common factor.
sorry, say again?
Is this equivalent to the greatest common factor?
Yeah, that'd be another equivalent way to say it. So common divisor versus common factor. It's kind of like going back to the top here where divides, multiple, and factor, really just saying the same kind of thing. So yeah, it'd be the same kind of concept. Other questions at the moment? That's a good one to put here just on the notes. GCD is synonymous to saying greatest common factor. Okay, and surely if I gave you just two integers, n and m, like 200, 183, just some random numbers, we could work it out. My go-to process is I get a factor tree going, I break it down into products of primes, find out which primes are common, and then there's my greatest common divisor or greatest common factor. But if you want to make a machine do this, here is our process. This is an old algorithm. It's called Euclid from the Euclid of antiquity. So the process goes like this. It's really terse code because it cites mod inside of it. We don't have to redefine it here. We'll have two positive integers, and there's a requirement for the formatting that m be greater than or equal to n. So I'll always pretty much put that format down. I'm not going to switch it on us to try to trip up the execution of this. So once we have two positive integers, and we put the largest one as the second one, m, we're going to output the greatest common divisor of both of them by doing the sequence of operations here. It's an if-else, and it's another recursively defined function. The else is going to call the function itself. Let's focus on the if part. It says if m mod n is 0, return n. In other words, we know the greatest common divisor is n itself. Here's a quick example just to think about what's happening on these first two lines of the syntax. Let's say that maybe n is 20, m is 40. So if that's the case, the greatest common divisor, the largest integer that divides both, that's got to be 20, right? 20 divides both, and you can't go any higher, or you're not going to divide n as well. So that's why we do this first check. Take m mod n, which is going to be 40, mod 20. That comes out as 0. And if that's the case, this tells us n is the greatest common divisor of 20 and 40. So that's the thinking on the first two lines. If we get a mod 0, we have our answer. It's just the first input to the function. But if that's not 0 in modulus, that means something smaller than both of these numbers, or excuse me, something smaller than 20 can potentially divide both. So we cite this. We take m mod n, that input right here is smaller than the n input in this case. If this is non-zero, then the result cannot be m any longer, or excuse me, n any longer. It's going to get smaller and smaller. We put in n here, and we run it all over again. We find if the greatest common divisor between both of them is just m mod n. And if it is, we'll return n. And if it isn't, we do another recursive call, and we keep going until we get a mod 0. Once that mod 0 happens, we've got the greatest common divisor. So that's the whole logic between the Euclidean algorithm here. And we'll try it out by hand. This will be for 24 and 82. We'll trace this execution just like we did for mod and div. And for fun, we'll just double check it here. Here's expand in syntax. I added 3 extra lines because I felt like, it's okay to throw in a larger input here and a smaller input here. So I did a variable swap to handle that case if it occurs. But the rest of it is pretty much verbatim what the author said. If m mod n is 0, we're calling our mod and div algorithm. Bracket 1 is saying just the modulus part. We don't need the floor on this one. If it comes out as 0, we'll return n. And if it doesn't, we'll take a mod n div of m and n, the input 1 for just the modulus, and cite Euclid again. So that's pretty much the same pseudocode as what you see here. Let's give it a try by hand, see if it works out, and then see what this would do if we ran this as well. Well, to get started, if you look really closely at that, some of us might know immediately what the greatest common divisor is. If you factored this, 24 factors as 2 times 12, so that looks like it's a 2 times 2 times 2 times 3. 3 doesn't divide 82, so looks like 2 might, or 4 might, or 8 might. So if you did a really quick check on that, 82 divided by 8 doesn't work. 82 divided by 4 doesn't work. So 82 divided by 2, it does work. Looks like the greatest common divisor should just be 2 itself. But let's see exactly what this is going to say if we traced this algorithm instead of using our own ad hoc algorithm that we might try. So first thing we're going to do on step 1 is we're going to run Euclid nm, which is 2482. So that's our n value, that's our m value. When we run this, here's the first line that's going to execute. We're going to do a mod. So on line 1, let's compute m mod n. Notice the switching that we have here of the inputs, the arguments to the function, and the modulus. It switches on us, so we have to be really mindful of the order on this one. So we'll go 82 mod 24. And just to save us a little time, we've done lots of modular arithmetic operations like this. Let's just call this function once again. 82, 24. That modulus comes out as a 10. We want it to be 0 because that means we're done, but this is not equal 0. So we skip the if block. We jump to the else block. The else block is executed. So on inputs 2482, none of this runs. We don't meet this logical condition that the modulus is 0, so we don't return anything on this step. We jump to the else block, and we return this instead. We're going to call Euclid with different inputs. So this means, let's say on our step 2, return. Well, let's see. Let's format this slightly differently. I want to format it by saying, if we execute this one, return Euclid. And we want to be, again, really careful with this input. It's m mod n, comma n. So we know our n is 24, so that's this one right here. We did a modulus, 82 mod 24, that came out as 10. So when we say m mod n right here, we mean that 10 altogether. So we're going to run Euclid 10 and n is still 24. Let me fix my handwriting there. So that's what happens on the execution of this one. We skip the if block, we return a new function call. The function call has smaller inputs, but now we need to run Euclid 1024. So that takes us to step 2. We go back to the top. We're running Euclid once again. We do another logical check here to see if we're in the if part or if we do the else part. But any questions at all, folks, on this first step? Okay, well, let's continue. For Euclid 1024, we check this condition. Take m mod n, but then be really careful because what we call m in this new execution of Euclid is going to be this value. What we call n is the first argument, 10. So this time we're taking 24 mod 10. 10 goes into 24 with a remainder of 4 going in 2 times. So our result is 4 altogether, which means that logical condition is false. This is not 0. And once again, we'll have the else block executed. So I'll say here, else block executed. When that executes, we make yet another function call, Euclid. We're returning Euclid m mod n and n. But these values are changing each time we go. When we say m mod n this time, that was based off these values, and the modulus came out as the number 4 now. So the values are definitely getting smaller. When we say n this time in this function call, we were referring to that n, or just for the sake of parallelism, I'll indicate it here. We're talking about that n right there at the 10. So that's our step 3. Run that particular function call. And again, it's good to go really methodical with this one. We practiced the trace with mod and div, but that one felt like it was just more kind of repeating itself in a very particular way of subtracting the same value, incrementing the same value. But this one, as soon as it's recursive, it feels like there's a little bit more going on. We have to keep careful track of every single function call. What are the actual inputs? And this gets even more hairy when we do the extended Euclidean algorithm in section 7.3. That trace becomes a real challenge. So think of this as kind of practice to get to that step. So next level, we do another, oh, hang on. We return this Euclid, but I never said what that function call was. Let's keep on going. This is going to be Euclid. Specifically, we're throwing in 4. And 10. So that's our next thing to do. We're running Euclid once again, very top. Go line by line. When we start here with the logical check, take m mod n. This time, here's our new n and m. M is 10, so we're taking 10 mod 4. Darn it, that's not 0, is it? That 4 goes into 10 twice with the remainder 2. But these numbers are getting smaller. This cannot go forever. This is going to end soon. But the fact that we have 2 here, which means it's not 0, it'll cause the else block to execute. So else block executed. That means we do the same kind of parallel step, but just with new values. Return Euclid M mod n and n. So that's this portion right here that we're returning. I'm running out of colors, but the highlighter will do the job. This time when we say m mod n, the value came out as 2 for that, and our n value is 4. So that means we're returning Euclid 2, 4. So that's going to be our step 4. And let me see if I can move this down. So calling Euclid 2, 4 takes us to the very top once again. We check this logical condition, m mod n. So let's put our handy notation down. This is the n and this is the m, just like before. So m mod n this time becomes 4 mod 2. But that's terrific. We know 4 mod 2 is absolutely 0. 2 divides 4, in other words, or 2 is a factor of 4. Many different ways to say that. But the modulus is 0. It came out 0 for the very, very first time, which is great because this means the if block is executed. And once the if block executes, we're essentially done. So let's say here, if block executed, return n, but we have to be careful. N is not 4. 4 is not the greatest common divisor. We return 2. Once again, that's the n value that we indicated all the way down in this process. As far as these kind of traces go, even if they get a little bit more involved, if you pay really close attention to carefully doing a couple lines, it feels like you're just sort of copying the process on the very next lines. So write one down really carefully and then just use parallelism to follow the format and the features all the way down to the bottom. So we're returning n equals 2. And that means, in conclusion, our goal was to find the greatest common divisor. We traced this whole thing and we found, therefore, greatest common divisor of those original numbers, 24 and 82, is in fact 2. So that's the Euclidean algorithm. This one, again, Euclid is a real person, thousands of years old, and this is a real process. So it's kind of fun doing mathematics from antiquity, essentially. We run it as a process here. Here's the Euclidean algorithm. Just cite Euclid. Get 24 and 82. And that's our value of 2. And it's got some error checking here. If you go 82 and 24, I mean, it's symmetric. That shouldn't change the greatest common divisor. Our author wrote this in a particular way to make the pseudocode brief. This one is extended to work even if you swap the size of the integers. So just as a reminder for the class, you don't have to run the pseudocode that we're posting on the notes. This is mostly for classroom demonstration. As far as a homework problem goes or an exam 3 question goes in this section, I'll ask you to trace things, but when you're doing it on the homework, it's not a bad idea to pull out a tool like this or code it up in C or Python and so on, just as a double check on your results to see if it came out right. Well, that's the end of the discussion on modular arithmetic. What we're going to look into next is this notion. If greatest common divisor of n and m equal 1, this turns out to be extra special in terms of properties of modular arithmetic. We'll say n, m are relatively prime. And once we find relatively prime integers like this, we can extend our properties here to a new property, finding an inverse mod k. So that's what the Euclidean algorithm is all about. we have to extend the algorithm even further in the very next section. And because relatively prime comes up, we'll do a short discussion on prime as well. Look into another algorithm, the sieve of Aristophanes. But any last questions or thoughts, folks, with the wrap up of this section? Okay, well, this is number theory so far. If you take any number theory textbook out, you'll notice that it goes pretty far pretty quickly. We're really just scratching the surface of number theory, but that's okay. The major objective is to see how a lot of our tools and ideas, thinking about algorithms, come together. And so this is going to be our next section. Once we complete our chapter 7 on number theory, we're going to have a new algebraic structure involving modulus. And that's going to be part of our examples when we look into relations and equivalence classes in chapter 8. So here's primality, relative primality. If we scroll through to see what our ultimate objective here is, we're going to talk about relatively prime integers and the extended Euclidean algorithm. This one is going to solve this property here on this lemma. The extended Euclidean algorithm is once again going to help show us how to take something to a negative power mod k. So it'll give us inverses, extending our properties. And this is going to be the challenge question. This trace, even for small values like this one, is kind of a monstrous one. So we'll make sure we practice it really closely. Well, all that starts off, because we're going to talk about relative primality, it's a good opportunity for a chapter on number theory itself to talk about prime numbers as well. So here's a couple definitions just to get us started. We'll say a number is prime if its only divisors are the number and itself. One is not considered to be prime. We'll call that neither prime nor composite. And an integer n greater than or equal to 2 that's not prime itself will be called composite. So those are our initial definitions so far. Any questions about primality at the moment? Okay. Well, we say numbers like, say, 4 is composite because it's made up of primes. It's composed of 2 times 2. And that's what the prime factorization theorem is called. Usually in a book on number theory, it would be called the fundamental theorem of arithmetic, which might be analogous to what you're thinking about, say, fundamental theorem of calculus. Linear algebra, there's a fundamental theorem of subspaces. So this is one of the major ideas in arithmetic itself. It says if you grab any integer that is greater than or equal to 1, then there will exist k equals greater than 0 prime numbers, p1 through pk, such that n can be expressed as a product of primes. And aside from reordering, because multiplication is commutative, you could reorder these primes. Aside from reordering, the primes that you come up with are unique. So that's our fundamental theorem of arithmetic. You can factor down any number in this kind of way. And one nice shout out to, say, strong induction is if you want to prove this, the uniqueness is its own thing right here. But the existence part, showing this factorization, that's just strong induction. And it uses all cases, P0, P1, all the way through Pn minus 1 as well to show the strong induction actually holds. So it's one of the big uses of strong induction. So there's our prime factorization theorem. And the big one we'll investigate a little bit more after kind of just putting everything on the table, talking about primes. Here's where some of our computations are going to start. A big result in number theory, the prime number theorem. So we're going to denote this thing here, borrowing the notation from the textbook. Primes n is going to be equal to the number of primes less than or equal to n. So whenever we see primes n, that's what we mean. So if we say primes 100, we're talking about the number of primes less than or equal to the number 100 itself. And we have a really interesting asymptotic behavior for the prime numbers. As n gets large, the ratio between primes n, the number of primes less than or equal to n, and n divided by log n approaches 1. So you can replace, if you haven't taken calculus, as n gets large, is just what this is saying here. As the limit of n gets bigger and bigger and bigger for larger and larger values of n, the ratio between gives us this fraction, and that ratio becomes 1. This has a couple of immediate consequences, and one consequence is that this means the limit as n goes to infinity of n divided by natural log n is infinity. And you can verify that directly. Like if you've taken calculus 1, just hit that with L'Hopital's rule. You get infinity really, really fast. But if you take this as a given fact right here, that the limit is infinity for this one, that n divided by log n gets larger and larger as n gets larger and larger itself, what's also telling us is that the number of primes is infinite. And it would be a really weird logical structure on a set Z if that wasn't true. If there was a finite number of primes, that wouldn't be the arithmetic we're all familiar with. That'd be something completely new, a new algebraic structure altogether. So altogether, we have an idea of what prime numbers are, what primes can do. They provide a factorization, and this prime number theorem is just telling us there are, in fact, infinitely many different primes out there. Any questions at all, folks, with just the introductory topic so far? Okay, example 1 is really just working with the prime number theorem a little bit more, trying to see what exactly it says. It asks us approximately how many prime numbers are less than or equal to 1,000,000. Well, it's an approximation problem, and we're not meant to calculate this exactly, so don't worry about being off by a little bit. We can do this approximation directly through the prime number theorem because this ratio, our approximation is really rough if n is, say, 50. That's not a great approximation, but this approximation gets better and better because the ratio gets closer and closer to 1 as n gets large. So the approximation is done through the fact that this limit comes out as 1, which is just another way of saying primes n is approximately that denominator. So we can set n is 1,000,000. Then, directly using the prime numbers theorem, by theorem 7.15, let's also use our author's notation, primes. N is the number of primes less than or equal to 1,000,000 will be equal to approximately n divided by the natural logarithm of n. So at this point, we just have to reach into a calculator. Here's a fast one, it's ready to go. And do that division. Take 1,000,000. Divide by the natural logarithm of 1,000,000. So for this particular calculator, if I say log, the base is automatically e. So that'll give us the natural log. So 1, 1, 2, 3, 4, 5, 6. And there it is. We'll absolutely round to the nearest integer because you cannot have a fractional amount of prime numbers. And it's approximation anyway, so rounding to the nearest integer would make the most sense. 72,382. So that's the number of primes less than or equal to 1,000,000. You know, there's an approximation here at that step, and there's also an approximation here at this step. I rounded to that particular integer. Any questions at all, folks, getting that approximation down on paper? Okay, one big question you might have is, what do you do if you wanted to actually count that figure? How many exactly primes are there between 1 and 1,000,000? One algorithm is the good old sieve of Aristophanes. We'll trace this one out by hand for a small number 40 just to see how it goes. But here's the actual pseudocode for running that. These things are not necessarily the most efficient algorithms whatsoever, but I think you might get that to run at 1,000,000 depending on your machine. Well, it looks like we ran out of time. Sorry for going over the minute. Any last questions or comments, folks, before we call it a day? Okay, well, have a great weekend, folks. When we come back next week, we're going to run through the extended Euclidean algorithm after getting through these arithmetic initial topics here on primes. And then we'll be very soon showing how to take the inverse mod k. That's going to give us a rounded algebraic structure. And then we're going to use that and use that in the next chapter. But have a great weekend, folks. We'll be back to it next Tuesday. Thanks. Have a good one.